generation of learning algorithms is history, maybe pre 1980s, 1980s and 1990s. In pre 1980s, we were having only linear decision surfaces. Okay. And in 1980s, neural networks and decision trees actually came, which actually allowed non-linear decision surfaces. And in 90s, you have efficient algorithms, maybe this SVM and other things actually came. So that's a history that they tells. And so in the okay, this we will skip. Okay, so now we will see what is actually SVM and how it is related to a neural network and how it is different from neural network ANN. Okay, so that's a basic idea. Support vector is just like a neural network. Okay, a one-layer neural network. So we know that whenever you are having a one-layer neural network and maybe a linear activation function, you will have a straight line as the decision boundary. Okay, when you bring in non-linear decision activation functions and more number of hidden layers, you will get a combinations of decision surfaces, and finally you will get a non-linear surfaces. So, so that's the way neural networks actually works. But the interesting point of SVM is actually SVM tries to solve the two category classification problem always using a linear decision boundary. Okay, it does not try to find out a non-linear decision surface, but it will solve that case in another way that we will come to see how it is actually trying to find out a non-linear decision boundary using a linear decision problem. So that is a trick behind SVM. Okay, so the optimal hyperplane for linearly separable patterns, okay, and extend the patterns that are not linearly separable. Okay, so that is not linearly separable. Not linearly separable okay, forms of data into map into a new space. That means we'll come to that point. That is SVM tries to map okay the set of points in the current space to another space, to a higher dimensional space, where you can find out a linear decision boundary. That means in effect SVM always finds out a linear decision boundary only. Okay, it will not go for a non-linear decision boundary, but it actually achieves a non-linear decision boundary through mapping to a higher dimensional space. So that is maybe in a way that is actually achieved through a trick called kernel functions or kernel trick. Okay, so that is actually the major difference between SVM. Okay. Then a few concepts of terminologies. Support vectors. So support vector machine, that is a terminology. But what is support vectors? They are actually training set data points, okay, that lie closest to the decision surface. Okay, the decision surfaces we have already seen, say decision boundary, decision surface, hyperplane, lot of terminologies for the same thing. Okay, so the data points that are closest to the decision surfaces are generally called support vectors. We'll come to that terminology later clear. And we can, in another way, we can say that they are the data points most difficult to classify. Okay, support vectors, because they are very closer to the decision boundary. Because you have to be very crucial in taking the decision, and they have direct bearing on the optimal location of the decision surface. And you can see that SVM always finds out the optimum decision surface. That's a interesting point. That's a difference from ANN. Okay, so we can show that optimal hyperplane stems from the function. So that we will just skip. That is not required. Okay, so now we'll come to the earlier problem. So from a one single layer neural network, that means one hidden layer and one the output layer. That's all. Okay, we know that we can easily straight line is actually W transpose X plus W0. Okay, so because if you are having one hidden layer, sorry, one input node, input layer and one output layer, the output layer is actually simply produces a straight line. Okay, that means you have a, if it is having a linear activation function, you simply get a W transpose X plus W0. Okay. So here is also which is a separating plane that's that will give you the best result. Okay. So here you have this particular dark and maybe this blue line. So I think from the figure we can clearly say that the blue is actually a better option. Okay, compared to the black one. Okay, so because that will give you a lot of space here, so that categories of these points falling here will not be wrongly classified. Similarly, in this case, these points, that means the blue points, you are having a lot of space here, so that other blue points that will fall near to this blue line will not be wrongly classified. But if you take the black line, it is very tight. If you have a point, okay, there's a chance that that will cross the boundary and wrongly classified. So that is a line that we are looking for, is actually the blue one. Okay, then what a SVM actually does is actually SVM actually maximizes the margin. Okay, the margin. So if you look into this set of points, that means you're having this square points and circular points. Okay, so if you look into, we can say that this red point that is near middle of these two parallel lines, that is the line that is passing through this gray colored circles, and the line that is passing through again this gray colored say square points, okay, and a line that is actually in between this particular these 2 points. Okay, so SVM actually tries to maximize its margin. Okay, it's a maximum marginal hyperplane, and the hyperplane that SVM returns after, say, the training phase is actually the middle, say, red line. Okay, so that is a hyperplane, but that is actually determined, okay, by these 2 parallel lines. And the importance of, or the significance of those 2 parallel lines is they are actually passing through training set data of the 2 different kinds, because here 2 points determines this particular line, and here 3 points actually determines this particular, and your maximum marginal hyperplane is actually equidistant from those 2 parallel lines. Okay, and the points, the training samples that determine maybe the position of these 2 parallel lines, and in effect that determines the position of the middle hyperplane, is they are called support vectors. So you can say that here you have a 5 support vectors, 3 of one category and 2 of other category. Okay, and a very interesting point of SVM is that suppose you remove all the training samples from the this diagram, okay, except the support vectors. That means only you keep only the 5 points and remove okay all the other points. Okay, even if you add, suppose you add maybe the new green points as well as the yellow, the blue points later. Okay, keep in mind that all the points will be maybe less than, okay, or the bottom of below these points and above these points, then you will get the same hyperplane, because the hyperplane is actually determined by the support vectors, not by the other training samples. So that is actually in a way different from ANN, because ANN, if you want to again recompute it, you have to show each training samples. You cannot actually take half of them and again retrain. There is no surety that you will get the same separating decision surfaces. So that's the beauty of SVM. That means SVM is actually not determined by the its number of points, but it is determined by the number of support vectors. So that is actually the problem. So the decision surface is actually function is fully specified by subset of the training samples called the support vectors. Okay, and there is a mathematical technical quadratic programming problem, because this SVM actually finds out this maximum margin hyperplane actually using a technique called a quadratic problem. So that we'll come to that later. Okay, fine. This also we have just seen. Okay. Okay, so here the input is actually a set of training samples and output is actually a set of weights, because here we are finding out Wx plus B. That's all. Decision surface we need to find out it's a linear one. So that means the weight values W for one for each feature, whose linear combination predicts the value of Y. So that means, because I already told SVM tries to find out a linear decision boundary. So it's a linear Wx plus B form, okay, equation that SVM actually returns. Okay, then what is the difference between say ANN is actually we use optimization of maximizing the margin, okay, to reduce the number of weights. Okay, so here we are actually not storing the weights corresponding to each of the component of the input vector, because we only store those weights corresponding to support vectors. So that is a very major difference. Okay, so that's very important. In that way, the complexity is actually reduced, but it takes a lot of time for training purpose. But after that, it is a very good choice. Okay. So that is one case. It's a two-dimensional case. Okay, fine. That we'll skip. And here also which hyperplane to choose. Okay, all this we have seen. Then, so support vectors are the elements of the training set. Again, the same thing actually. Okay, and they are the critical elements. Fine. And now the problem of finding. Okay, so the problem of finding optimal hyperplane is an optimization problem. Again, it's an optimization problem because you have to find out the best W weight vector. Okay, which will actually reduce the error. Okay, and it can be solved using an optimization technique. Okay, through a technique called Lagrangian multipliers. Okay, here also we will not go to the mathematics behind it, but using the principles of Lagrangian multipliers is the way the optimization is actually done. Okay, so this is this picture will make the points more clear. Okay, so here you can see that these two circles and one cross. There are three support vectors. Okay, and you can have the equation for the two parallel lines. That means the hyperplanes or the hyperplanes that are passing through the support vectors. Okay, they can be represented as W0 transpose x plus b0 equal to 1. The same equation. The only thing the format is different. Again, W transpose x plus b is equal to minus 1. Okay, so one is going through plus 1 and another one is minus 1. Okay, they are the two parallel lines that determines this black line, which is actually say is a decision surface, a hyperplane. Okay, so here you have three support vectors. Okay, and finally, so here also you can see that it is equidistant. So that is also the same thing. Okay. So then how the hyperplanes are defined is actually W x1 plus b greater than or equal to plus 1. Okay, for one category. Okay, suppose h1, you have a h1 here. Okay, and for this particular h2 case, okay, you have a ws plus b less than or equal to minus 1. That means less than minus 1. Okay, you have one these green points, and greater than or equal to plus 1 represents the red points. Okay, and here you have a 1, 2, 3, 4, 5, 6 support vectors, 3 of red category and 3 from green category. And the middle line is h0, which is actually the hyperplane, which is ws plus b is equal to 0. Okay, so you have a gap here, so that it is equidistant from your central line is equidistant from the nearest training samples of each category. So that you'll have a lot of generalization error will be minimum. Okay, for both the categories, not for a single category. So that is a shortest distance. Okay, so this is also not the very important. So it's also W transpose S plus B, the same equation, the same thing is actually explained. Margin of separation is D. Okay, again, optimum margin means maximum margin. Okay, because that will give you the best error. And now we will see. Okay, the same equation that is actually called that is Ws plus B greater than or equal to 1 and Ws plus B less than or equal to minus 1. Okay, so this is actually can be represented as a quadratic programming problem. So what is actually here, we know that we have to maximize this width. Okay, this width between the support vectors. Okay, the line. So that is actually we can represent the total distance between h1 and h2 is 2 divided by modulus of w. Okay, because 1 by modulus of w, this particular half a, and this is half is again. So that you will have a 2 divided by modulus of w. Okay, and so we have to minimize that modulus of w, because we have to maximize this particular distance. So we have to minimize this modulus of w. So it's actually minimize modulus of w, and the same can be represented mathematically. Okay, and there is a constrained optimization problem, and there is a constraint. Constraint is actually ya into ya is actually the class level, and wx is actually the weight vector into the input. So minus b is actually the bias, minus 1 is equal to 0. This is a condition. So it is actually a optimization problem. You have to optimize the minimize the modulus of w with respect to this particular constraint. It's a constraint optimization problem. Okay, so we are not going to the mathematics. Okay, it will take maybe another 2 hours to discuss. So just okay, here another advantage is that SVM always find out the best optimal one. If you will not have a global, you'll not have a local minima. Okay, problem here. Okay, so here also we'll skip. It is easy to, if you go through, it is very easy. Okay, so I'm skipping all this because this explains a quadratic optimization problem. Okay, so just skip it, and we'll come to the towards the end of this SVM. Okay, so this is a not linearly separable case. Okay, so not linearly separable because you can see that the points of different kinds of crosses. Okay. You can put a penalty, okay, and say that we allow 5 points to cross. Okay, but there are too many points, okay, mixed up. Then you may not be able to put a penalty. But how SVM actually solve this problem is, suppose on the left side you are having a but mix of points where you cannot draw a straight line. Okay, but you can draw a curve like this, okay, which will be able to classify the points, okay, above the line one category and below the line another category. Okay, so SVM, or what, this is non-linear decision boundary. But how SVM does is actually this is SVM actually maps the given set of points on the left side to using a function, say psi or phi, whatever it is. Okay, it is transformed into a higher dimension space, so that say all the 0 points, okay, represented as zeros coming below the separation line, and which we call it a hyperplane, linear hyperplane in that transform dimension, and all the x points actually on the other side. That means on the transformed space, the points are actually linearly separable. That means SVM always finds a linear separation only, but before that it actually maps the points to a higher dimension. But now there's a challenge, which higher dimension is actually will help you to find out a linear decision boundary. That's again a challenge. Nobody can actually say predict also. It's actually again a prediction problem. Okay, but it is almost impossible when the number of dimensions actually increases. Okay, but there is a turnaround, was a trick by SVM. We'll come to that. So here you can see that this again the red points and blue points. So here we cannot draw a line to separate it. But if you map this into a parabola or into a second order polynomial form, okay, say something like the bottom figure, then you may be able to draw a straight line where we can say red points around the on one side of the decision boundary, and the blue points around the other side. So then you can say linearly separable. Linearly separable means you can draw a line there. So it's a non-linear SVM. Okay, so it's a problem. You cannot draw a straight line here. Okay, maybe a circle is fine, but nobody knows whether it's because as the points are plotted and easy to understand, we can easily say it's a circle. But mathematically what has to be done is we have to map to another dimension where it can be easily separated. So that's the idea, non-linear SVM. But the non-linear SVM actually avoids finding out the highest dimension, or the dimension to which we have to map in order to get a linear decision boundary. Is avoided by applying a kernel function on the input data itself. Okay, so you don't need to. There is an equivalence. That means applying a mathematical function on the input space itself is equivalent to mapping the input space into a higher dimension. Okay, so that's a equality, mathematical equality. So that means you don't need to transform to higher dimension, which is almost difficult to find out which dimension, but you apply some kernel function. dimension, so that will be mathematically equivalent to solving, okay, to higher dimension. So that is called a kernel functions. Okay, so there are many kernel functions of polynomial kernel, okay, which is defined as xi into xj. So xi and xj are actually on the input space itself, not on the transform space, because if there is a 4-dimensional data, sometimes your transform dimension may be 10 dimension or a 20 dimension. Okay, so that means when you multiply two vectors, okay, it will be say 20-dimensional calculations you have to do there, but in the input space you have to do only 4-dimensional calculations. So there are many kernel functions that are existing. So the most common is actually called a polynomial kernel. X and y are input points. Xy plus 1 always should be okay, and or you have Gaussian function that is called a radial basis function, and you have a sigmoid function, the one that we have seen with ANN, artificial neural network. It's a neural network activation function called a sigmoid. That's a tan H function. So these are some of the kernel functions, okay, that will help you to solve the nonlinear SVM. Okay, so that is called a kernel trick. It's a very important. Again, that will take a lot of time to discuss. Okay, the mathematics behind it. Okay, so that is actually the idea behind it's a nonlinear RBF function. You can see that difference. Okay. Okay, so that is actually about SVM in a quick way. Okay, so we are not going to the mathematics behind it. So I think with that we'll wind up this session. Okay, so thank you, sir, for inviting me and giving an opportunity to share my thoughts on ANN and SVM. So thank you for kind listening by the participants.
Thank you, sir. Thank you, sir, for the session. We'll have some. Shall we take a few questions?
Yes, yes.
Yes. Okay. So from the audience side, if any questions are there, you can raise it now.
Hello.
Hello.
Yes, I'm audible, sir.
Yes, please.
Yes, sir. This is Pooja Gandhi. I'm the research scholar. I'm facing one problem while I try to fit my support vector regression model on diabetes data.
Okay.
Okay. I posted on this Stack Overflow on the Quora as well. I don't know why I'm not getting the training accuracy. I'm getting training accuracy only 30%.
Okay. So
Can you have any suggestion, otherwise any website related to this?
maybe you may mail me, okay, the issues, so that I can give you some suggestions over email.
Okay, okay, sir.
Okay.
Thank you, sir.
Thank you.
Okay.
Okay. Is there any more questions? If no more questions are there, we'll wind up the section now. If there is one question coming from on the chat: how SVM optimization algorithm supports for medical imaging in cancer detection?
Yeah, actually, supports in the sense whether it is actually any problem, the SVM is actually the optimization is actually working based on the same principle, because whether it's an image or whatever input, you are actually representing the data as a vector form. So whether that is medical image problem or some other image from where you are actually extracting the features is immaterial. Okay, so the SVM optimization is actually the maximum marginal hyperplane. Okay, and that is actually found out using maybe the maximizing the distance between the two hyperplanes that are passing through the support vectors. So that is a basic working principle of SVM, whether the problem is from domain 1, domain 2, or domain 3. So I think SVM is one of the best algorithms. Suppose if you're not going for any deep learning techniques, because deep learning techniques you need a lot of data. Okay, and there are some shortcomings also there. Okay, you cannot apply, but small medical data is very limited only. So may not be possible to apply. So in such cases, SVM may be the best option. Okay, I think that's a way.
So I think we don't have any other questions now. So I think we can we'll wind up the session now. So sir, thank you sir for having given an informative session on SVM and ANN based methods. Thank you for spending. It was very informative, and I think all the participants must have taken good takeaway from the session. So thanks to Gopakumar sir from on my behalf and from all the participants. Okay, thank you, sir.
Thank you all. Thank you all. Bye.
Bye.
Bye.